Hey, my name is Jan Ketil Raut, and I will in this video continue to talk about representation, but with an emphasis on the discrete object view and the use of vector data. Most of the content in this video is taken from chapter 2 in the textbook GIS Tools to Understand the World. Vector data uses three types of geometries: points, lines, and polygons. A polygon, or an area, is one closed line or a collection of lines that encloses an area. A line is a collection of points that constitute a line. So no matter which type of geometry in vector data, the point is the minimum unit. The most important characteristics of a point is its location, given by a pair of coordinates. Coordinates can be given by spherical coordinates like latitude and longitude, or as here, according to a Cartesian coordinate system. Here we have an x-axis which gives the position in an east-west direction, and an y-axis which gives the position in a north-south direction. And this relates to the origin having coordinate 0, 0. A line is a collection of points and thus a collection of coordinates. So we have here a line with coordinate 2.9, the first one here, the next one 6.7, etc. A line always starts in a node and ends in a node. Lines therefore also have a direction, a left side and a right side. Points that are not the start or the end of a line are called vertices. If the first and last coordinate of a line or a collection of lines is identical, that means that the line or collection of lines constitute a closed area. If, however, there is a gap, no matter how small the gap is, if the start node and the end node of that line that is supposed to be a polygon is not at the exact same location, it is a line. Now, when representing reality around us, we need to reduce geographical feature to discrete objects. So, whatever you wish to represent, it needs to be represented using points, lines, or polygons. And here are two examples of features in our urban environment that are typically represented as points. We have an outlet where the surface water will drain, and a manhole that enables access to the water infrastructure and possibly other infrastructures. Other examples of feature often represented as points include a glass container, a light pole along a road, and a flagpole in someone's garden. Examples of features typically represented as lines include power lines and roads. But roads also occupy large areas, so depending on the scale, roads are often also represented as polygons. However, irrespective of scale, for route planning, roads are represented as lines. Each line starts and ends with a node, but a node is also a point where two or more lines are meeting. One line's end node is another line's start node. And the example show one line here because the start and end nodes, this line has a direction, and the GIS then knows that these lines continue in three other lines. This is true for what we call topological structured line features, which are rules that enables network analysis, such as route planning, how to get from point A to point B. Now, other examples of features typically represented as lines include paths and open ditches, often found along roads. Then the third geometry types, polygons or area. Here are examples of features often represented as such. Roads are often represented as areas, so as well forest, fields, canals, lakes and other large water bodies. This figure is an illustration reproduced from Jan Terje Bjørke's lecture notes in digital cartography. And this is showing the components of geographical data stored as vector representations. Geographical data consists of both spatial data and attribute data. The spatial data has positional data given by coordinates and a geometric form given as either point, line or polygon. And attached to the spatial data there are attribute data, data that describes the points, lines and polygons. So all three geometries therefore has attribute tables that store the descriptive data. A point layer, for instance of capitals, will typically have an attribute table having descriptive information about the name of the capital, which country it belongs to, and a country code. A linear layer of, for instance, international boundaries will typically have descriptive information about which country it separates, which country is on the left-hand side and on the right-hand side of the boundary. An example of a polygon layer is a layer with land use categories, such as built-up area, forest, lakes, etc. We often say that the polygon layer is two-dimensional since it occupies space. The attribute for a polygon layer therefore has a field for the area and one for the perimeter. We say that the line feature is one-dimensional since it does not occupy any space, but it has a length. The attribute table for a linear feature therefore has a field for the length of the object, such as the length of international boundaries. Points are zero-dimensional, so the attribute table for a point layer has no data about its area or length. Now, one modification I've done by Bjørke's original illustration is the addition of the third dimension, the Z coordinate. For a long time, all GIS were flat, two-dimensional, and the attribute table showed then no information about any heights. The first attempt of introducing the third dimension was by adding this information as an attribute. Like here, an attribute of coordinate heights, the Z value. This was typically done by contour lines and lakes. Having the Z coordinates as part of the shape geometry is becoming the standard for most official vector data. At least this is so in Norway. The benefit of having the Z coordinate as part of the geometry is that there will be one Z value for each vertex belonging to the feature. The difference is demonstrated here. With Z as an attribute, the entire line would be displayed as having the same height. This is shown then for the red line. For contour, this was not a problem, since a contour by definition is a line going through points of equal heights. However, for a path, having one Z value for the entire line would not let the path follow the terrain. And having Z value stored as geometry, as shown by the orange line, all points belonging to the line would then have individual Z values and the line would nicely follow the terrain. This is the line from the previous example, showing then for each vertex that there is storage for also a Z value. And the line will therefore not appear flat if visualized in a 3D visualization software. It will nicely follow the terrain. Also for polygons or lines, each vertex belonging to the object has a Z value. Another characteristics of vector data is that the three geometries are kept separated. You do not mix them. Points, lines and polygon are separated in different layers. For For instance, water bodies, these are represented as both lines and polygon, but you use one layer for the linear features, such as the small streams, the ditches, and you use another layer for the polygon features, such as the large rivers and the lakes. Attribute data is connected to spatial data, and therefore in Björke's illustration there is a connecting line here. This is to simulate what happens when we read a map. Many will interpret, for instance, a blue line on a map as a stream. This interpretation is done based on experience, or one can also refer to the legend, giving the explanation that this is indeed a stream. For a computer system, however, such as a geographic information system, to know that a particular line is a stream, this must be coded. And a similar connection must exist in the data structure. This is done by attaching descriptive data to the geometric object, that is attribute data, being linked to the spatial data. All objects are therefore assigned qualitative and or qualitative data. Let's give one example of qualitative data. This could be land use categories, typically shown in topographic maps. Qualitative data provide information about differences, such as a yellow area representing an agricultural field or pasture is different from a green that represents a forest, or a blue representing a lake, or some gray one representing roads, or brown one representing buildings. Quantitative data provide information about relational proportion and is given on 3 measurement levels known as ordinal, interval, and ratio. In most situations, the differentiation between interval and ratio has few practical implications. This is an example of quantitative data on the ordinal measurement level, namely erosion risk. This can be divided into 4 classes: small risk, medium risk, large risk, or very large risk of erosion. And this is then in the map symbolized according to the metaphor: the darker the higher is the value. Thus the darker the purple color, the higher is the risk of erosion. This is an example of quantitative data, and it might be disputed whether this is interval or ratio level of measurement. If we would be strict, the depth of the sea may be best considered to be an example of interval measurement level, since we here may not have an absolute reference for 0. It all depends on what kind of datum we are using. However, there are seldom any practical reason to separate these 2 levels of measurement, and for this example, most would agree that the depth of 100 meter is double as deep as the depth of 50 meter, which is a statement possible to make for ratio data only. Discrete geographic objects can be identified by their dimensionality. With dimensionality we mean the space that the objects occupy. A point is an object of no area, no length, hence it is 0-dimensional. A line is an object having a length and is thus denoted as 1-dimensional. A polygon occupies an area and we thus denote it as 2-dimensional. Very recently we also have a 3rd dimension, the volume. So it has been for a long time able to extrude objects used only for visualization, but some GIS now have true 3-dimensional objects, enabling us also to do 3-dimensional analytical tools, making, for instance, intersections between volume objects. The temporal dimension, however, is still not, according to my knowledge, good. A criticism towards GIS, which very much still is true, is that it is static. It represents only a snapshot in time, and indeed representing the temporal dimension is, to my knowledge, not something which is implemented in commonly used GIS. There are, however, several examples on representing the temporal dimension as part of the attributes. One such example is the C-shapes dataset that shows the history of national states, their capitals, and their boundaries. Here, each polygon is having a start year, for instance, when the African countries became independent, and an end year, for instance, when the country stopped to exist because it was separated into smaller units, as was done for Sudan and Ethiopia. The end year is not necessarily when the country stopped to exist, but it may also be the version of the dataset. Here, the end year is showing 2012, and this is because the dataset is the 2012 version. For vector data, we have both spatial and attribute data, and these parts are linked. How this link is functioning is demonstrated here. If you select an object in the spatial domain, the map, for instance Norway, the corresponding row in the attribute table is highlighted. And this also works the other way around. If you select a row in the attribute table, the corresponding object in the map is also highlighted. The general rule here is that one spatial object is linked to one row in the attribute table. There is one exception for this, and that is multipart features. And multipart features is when we have several objects that are combined and connected to only one row in the attribute table. And this is very commonly done for municipalities, such as municipalities representing a collection of islands, such as Frøya, which consists of one big island and many small islands. And yet it is beneficial to treat this as one object when you in the attribute table has data such as the number of people working in the primary sector. There is a huge benefit of this link, and one of them is that you can make thematic maps. How a variable may vary geographically, it's very difficult to read by just looking at numbers in a table. But when this table is linked to a map, you can show the geography of the variable. Again, using the metaphor, the darker the color, the higher the value, you can see the geography of the variable. And here we have make a thematic map of a variable of life expectancy. This map is showing the geography of life expectancy, how long you may live, according to data from the World Bank's development indicators. Higher value we found in Western Europe, and there is a belt of medium-high values in Central Europe, as well as in Northwestern Africa. And we have lower value in Northeastern Africa, as well as in Russia, Belarus, Ukraine, and Moldova.